Okay, so we've been working on this idea of a g function, an area so far function. What's the variable we've been using as the input for that?
X.
And then what's our definition of the g function?
The g function is a definite integral from 0 to x of f of t with respect to t.
That's good. It's kind of a weird function, but that's the correct definition. Very good. Okay, so this is what we were talking about last time, and now we need to build on top of that material. So to start, let's start by answering this question, and then we can build on top of that. So try writing down an answer for this question on your screen, and then we'll show what the next steps are from that.
Okay, and then
Good. I guess I didn't put any numbers on here, so all you can do is just kind of label the graph. That's good. Good.
and yeah, so I guess this kind of answers the other question.
Yeah.
Where g is increasing and decreasing.
Okay, very good. All right, I'll go back to my screen. That's what we were working on last time. Very good. So you split this up into some key intervals. We saw that where f is positive, that means that the area so far is increasing. And where f is negative, the area so far is decreasing. And then f goes back to being positive here, so the area so far goes back to being increasing. And then this point here, we can say two things about it. One thing we can say about this point is that it's a local max of g, and it's also a point where f equals 0. And then this is a point, a local min of g, and it's a point again where f is 0. So where f is 0, those are the candidates for where g might have a maximum or a minimum. Okay, so what we were talking about at the end of our last session is that this is actually a very suggestive graph because it looks like f is acting like the derivative of g. These are the same types of graphs that we got when we were doing the derivative chapter one chapter ago. We saw that when derivatives are positive, the function is increasing. Where derivatives are negative, the function is decreasing. And where the derivative is 0, that's a candidate for local min and max. So this suggests that maybe f is the derivative of g. And that turns out to be the case. So we're not going to prove that, but we've suggested that from here. So what we can say is that f prime f is the derivative of g. Okay, which is suggested by these types of graphs. That turns out to be quite important. So now let's try to write that out as a theorem, because this turns out to be what's called the fundamental theorem of calculus.
So I noticed they use a couple different fundamental theorems. Is this one or two, or is it both?
So yeah, that's a good question. This is the fundamental theorem of calculus, part 1. So it's like a successful movie franchise. The first part was so successful they came out with the second part. So later on we'll be going to the sequel. But right now, as would seem logical, we're dealing with part 1. So that's right. Your textbook splits this up into parts 1 and part 2. So here we're going to be doing part 1. Okay, cool. So let's try to write that out carefully. As you might have perhaps guessed from this name, this is a somewhat important theorem. So let's see. We could write it like this. Here it is. This is the fundamental theorem. And tell me when you have that written down.
Yep.
Okay. Now, hopefully you agree that this is just a more fleshed out way of writing what we were already guessing earlier. Remember, we were already guessing that f was the derivative of g. That was what was suggested from these graphs, that f was the derivative of g. And then the fundamental theorem of calculus confirms that f is the derivative of g. F is the derivative of g. Okay, so there we go. Let's see. So is x here a variable or a constant?
X is a variable.
So is this a variable or a constant?
It's a variable.
How about this?
Variable.
Now, actually, remember that we usually use letters from the beginning of the alphabet as constants. And that's what the A is standing for here. Actually, in this case, the A is standing for a constant. After all, this function g can only have one input. So remember, this is what's called the area so far function. In the past, we looked at areas where we started at 0. But we don't actually have to start at 0. You could also do the area so far that starts at any point A. In the past, we simplified by saying that we were doing the area so far starting from 0. But it turns out the fundamental theorem expands that and says you can do the area so far starting at any constant A. But in any case, the point here, A is standing for a constant. It's the upper limit that we're changing. So we'd say that, for example, we could start here, and then if we move just a short distance, the area so far would be this. And if we move a larger distance, the area so far would be this. So here's two different x's, but notice that A is staying in the same place in both of those cases. Okay? So is this a variable or a constant?
X is a variable.
And how about this?
A variable.
This is the same thing I was pointing to before. And how about this?
A constant.
Yeah, this is standing for a constant. Remember, we have to see that letters don't always mean the same things. Okay. Now, maybe another way that we can write this theorem, would you agree that we could also write that would you agree this is the same exact thing as we have written up above?
The derivative of this function. Yeah.
So these mean the same thing. Because here we said g, the derivative of g is f of x. The derivative of g is f of x. But what is g?
G is...
What's the formula for g?
G is what's below.
G is this.
Right.
So This here is g. So this is just a more fleshed out way of saying the derivative of g is f. I think in some cases, though, this is better because you can use this version without actually inventing a new function g. This is a little bit simpler because now we don't have a new letter g. We can just put this directly. So notice something that's interesting here. The derivative of the integral of a function is the function. Okay. The derivative of the integral of f is f. The derivative, what this is basically telling us then is integration and derivatives undo each other. So, they're inverses of each other. If you take the integral and then you take the derivative, you get back to where you started. You were saying?
Yeah, I guess this is basically what we were doing before, where if we took the antiderivative of a function and then we could check to see if we got it right by taking the derivative of the antiderivative, and that should give us what we started with. Is that the same thing here?
That's a good point. Yeah. So that was also a case that showed that those were inverse. So what you're saying is that earlier we saw that the derivative was the inverse of the antiderivative. Mm-hmm. So yeah, earlier we saw that the antiderivative is the inverse of the derivative. However, this is actually much more surprising and interesting because notice, remember, this symbol isn't defined as an antiderivative, it's defined as an area. So no one would be amazed to hear that the antiderivative is the inverse of the derivative. No one could call that a fundamental theorem. It's not a fundamental theorem that the antiderivative is the inverse of the derivative because it was defined to be that way. But the thing that's amazing and surprising is that taking the derivative is the inverse of finding an area. That's not obvious at all. And we're not going to prove that. We're not going to prove that. It's proved in the textbook. But that's kind of an amazing fact that you wouldn't have predicted ahead of time. That's the key discovery of calculus. So calculus was invented in the 1600s by Isaac Newton, who you probably heard of was a famous physicist. So calculus was invented by Isaac Newton and Leibniz, another guy as well. And their key insight was that taking the derivative is the inverse of finding an area. If you start with the function, and then you find the area under the function, and then you take the derivative of that, you get back to the same function. That's not obvious. That's not obvious at all. That's something they had to figure out. So we're not going to prove that. We're just going to have to accept that discovery there. Since I mentioned a little history, it's worth mentioning, I think what Newton actually cared about was physics. But he got to a point in his physics problems where there wasn't enough math to figure it out. So he just said, well, I'll just admit calculus, I guess. So he just put the physics aside for a while, and he just invented this whole new branch of math. And then he said, okay, great. And then he went back and used the calculus to solve his physics problems. Wow. And obviously, we're not going to go into the details of that, but we've started to see how calculus could be useful in physics, right? Because we've done problems about velocity and acceleration and motion. Those are obviously simpler than what Newton was working on, or they're related to what he was working on. So we've already seen how calculus can be useful for physics. But anyway, I think he just kind of invented calculus as a sideline to help him with his physics. Okay, so in any case, let's see. So we were saying this is actually pretty surprising because it's saying that taking the derivative is the opposite or inverse of finding areas. That's not at all obvious, but we'll accept that that's true. Okay, and we did kind of suggest it was true with these types of graphs here, but let's go forward and see how we can solve problems with this. So let's see. All right, so that's our equation. So let me start showing how we can solve some problems with this. So let's try this. Since I mentioned that history, I guess I might as well mention. I was mentioning a second ago that Isaac Newton figured out calculus at about the same time as this other fellow Leibniz figured it out. Mm-hmm. I don't know if your instructor mentioned in class, but there was a huge argument after that about who figured it out first, unfortunately. So it was not very dignified for these titans of science. They were bickering at each other for the rest of their lives, or at least their friends and supporters were about who was it that discovered the calculus first. So it was a mixture of impressive intellectual accomplishments and kind of petty bickering. Okay, so let's see. So the function here is
it's definitely interesting, but I guess maybe they should have a history class for math. I don't know.
Yep, I'm sure they do, but I'm sure they do, but it's not a requirement for things that people are interested in, so people don't usually go into it. So, but tell you the truth, a class can make almost anything uninteresting. So it's much better when you're interested to just look into it on your own. Okay, so let's see here. Okay, so tell me when you have that problem written down.
Yep.
Okay, so I will simply demonstrate how to solve this problem. Well, oops. Well, first of all, I've got to write it correctly. So I messed up. Remember that we actually have to use the variable t inside of the integral. So I messed that up. Did I get that right now? Okay, now I think I have it correct. Okay, so they're asking us to find the derivative of g, but you can see here that g is just one of those area so far functions. So this is a good chance to use the Fundamental Theorem of Calculus, part 1. So what we've seen, and it turns out to be very simple, remember we saw that the derivative of this function is just the function. So I guess I could start by writing it. Well, I won't even do that. I'll just do this. Okay, and then we're done. So it took a lot of effort to discover the Fundamental Theorem of Calculus Part 1, but it's actually not too hard to apply it for solving problems. That's one reason why it's such a great theorem, because it makes it very easy to solve problems that would otherwise be pretty complicated. So that's all there is to it. What we saw here is that if you start with a function and you take its definite integral and then you take its derivative, you just get back to the function. I think the one thing that's tricky here is notice that we switched from t to x. That's kind of a tricky switch. I'm not even quite sure myself what the best way is to explain why that is. But g is a function of x, so our answer has to be a function of x here. So that's, I think, the one tricky thing. So you take the function, so the point here is, and that you can see that from the theorem. Notice that the answer is f, but you plug in x. The derivative is f, but now you plug in x. T is a variable that only has meaning inside of the integral. Outside the integral, we have to plug in the x. Okay. All right, do you see how I got this?
Yeah.
Okay, all right, I'll write down another problem then. Okay, try this problem on your screen.
Is that supposed to be g prime of x?
It sure is. Okay. I've been telling you to be careful with the x's and the t's, and I'm not being careful. So that's good. That's good that you were careful and caught that mistake. That's right. I was just telling you that t has no meaning outside of the integral. So you're right. I should have written it like that. Thanks. All right. So this is the problem.
Okay. Okay.
Okay, excellent. There's really not that much to it once you start working on it. Excellent, very good. By the way, notice we don't need to do that plus c here, because the plus c is when you're finding antiderivatives, but we're finding a derivative here. We're finding the derivative, so there's no point putting in a constant. The constant's when you're finding antiderivatives. Okay, so once you get the hang of the pattern here, these are pretty simple problems so far. You did that correctly. I'll go back to my screen. So you can do that kind of mechanically, but remember that the deep meaning of this is that if you start with a function and then you find the area so far of that function, and then you take the derivative of that, you get back to the original function. That's not at all obvious, but that's what the fundamental theorem says. Okay, good. By the way, one thing that you might want to start doing is when you're writing your t's, you mentioned before that t's can tend to look like pluses, so it might be good to get in the habit of putting on these little tails at the end so we can avoid those confusions. Okay, very good. Okay, well, sadly, the problems get a little bit harder than this. Not super harder, but a little bit harder. So let me show you another variation. There's another kind of, there's another way that we could define a area so far function. We could do a different kind of area so far function that looks like this. Maybe I shouldn't call it the area so far. What would be a good name for this? I don't know. Area, I don't have a great name for this one. It's harder to define, but it's the area from a shifting starting point. So do you see the difference between this and the previous function? In the previous function, we had a set starting point, and then we were moving further and further to the right. Well, here we have a set ending point, and we're changing the starting point. Okay, that just turns out to be another type of function that's interesting to deal with. And it turns out that your instructor likes to ask questions about what the derivative of that would be. And it turns out the derivative of that, we're not going to explain why this is. To save time, we'll just memorize this. That's not too hard to prove from the fundamental theorem. So this would just be this.
Okay, so this is going backwards. That's it.
Well, I don't know if we're not going to spend too much time on this. This won't be too important for the rest of the course, so we're not going to overthink this too much. This is just another, I'll just say this is another type of problem you could be tested on. This is a slightly different function because, like I said, this is a function where they hold the right point constant and change the left point and figure out the area underneath it, and that has a different way of taking the derivative. But to tell you the truth, it's not really worth our time to meditate too much on exactly what this means. We got more important fish to fry. So we're just going to learn how to do this type of problem so that we can get it right on the test, and then we'll move on to the more important stuff. Okay, so if you see this type of problem, we'll just say this is the mechanical way to solve it. We won't worry too much about understanding this in depth because we got other more important stuff to get to. Okay, any case though, do you see the difference between, how do you know when to use then this formula and when to use this formula? Well, let's review. Is this a variable or a constant?
Constant.
Is this a variable or a constant?
Variable.
So when the variable's the lower limit of integration and the constant is the upper limit of integration, that's when you use this formula. On the other hand, is this a variable or a constant?
Where are we? Oh, variable.
Is this a variable or a constant?
Constant.
So we'll just mechanically learn that when the variable is the upper limit of integration and the constant is the lower limit of integration, that's when you use this formula. Okay. All right, so this is a relative or a corollary of the Fundamental Theorem of Calculus, part 1, and we're just going over it because you'll probably see a test question about that. So I'll show you how to use that. So suppose we had g of x equals, let's say, 7x. Then we have x divided by x plus 2. I keep making that same mistake. This should be a t. dt.
So it's okay to answer these in one line like that? Just
let's see. Well, this was the question still. And now here's the question. Here's the given. Here's the question. And I'll just demonstrate. Yeah. So I think in this case, if you wanted to, you might, I think this is fine to answer just in one line. So using this formula. So the first thing is to notice, well, I'll just rewrite the function with an x instead of a t. And then the only question is, should this be plus or minus out in front? Well, I noticed that here the variable was the lower limit of integration. And we know, we've just memorized that when the variable is the lower limit of integration, that's when you put the negative sign in front. Mm-hmm. So I think that should be full credit right there. Okay. There really isn't too much to these if you do these kind of mechanically. But even so, I still screwed it up. So this shouldn't be a t, this should be an x. So that is the one thing that's easy to make mistakes. The t's only mean something inside the integral. Outside the integral, we've got to use x. Now I think I got it correct. Okay, does that make sense?
Yep.
All right. Okay, try this one on your screen. Okay, good. Sorry, keep going.
Okay.
Okay. Now, you actually did something here that was very good. You put in those parentheses. Those are totally necessary. Without the parentheses, the answer would be wrong. So that's good that you thought to do that. I hadn't demonstrated that, so that's good that you saw we needed that. Do we need to add a plus c?
No.
Because we're not taking an antiderivative, we're taking a derivative. Good. Okay, that's the correct way to do it. Now, how did you know to put a negative sign in front? When we did the earlier examples, we didn't put a negative sign in front.
Right, because in this example we have two terms, and we have to make sure they're both negative.
I think you're answering a different question than I asked. So I wasn't asking why we need the parentheses. I'm asking why we need a negative sign.
Oh, sorry. It's because the variable x is on the bottom here, and if it's on the bottom, we use a negative sign.
Okay, that's right. We didn't really explain why that is. We're just memorizing that for the test. Okay, very good. So that's correct. Good. So you got that right? Good. I'll go back to my screen. So actually, going back to my screen here, if this was a test question, I actually would have been safer to have written this expression. Well, in this case, you probably don't need it. In this case, you don't need it. But if the answer had been something like this, it would be safer to put in the parentheses so the reader can tell for sure the negative refers to both the x and the 1.
Okay.
Here, I think it's pretty obvious, so we didn't need it. Okay, well, we're not quite done yet with this fundamental theorem part 1. There's one more variation that's a little bit trickier, so I'll show you that. And again, this is real likely to be on the test based on the sample test, so let's see how to do this. Okay, so how is this different from the previous examples? And the question is to find g prime of x. So why can't we just use the earlier method? Okay. How is this different than before?
Let's see. Well, we don't have just the variable. We have 4x.
Yeah, we don't just have x, we have a function of x. Now, I think something that we learned earlier in the course is that our simple derivative rules only work when we only have a single variable by itself. If you see what I'm saying, we saw that lots of our earlier derivative rules only work when there's just one single variable all by itself. They don't work when you have a function of a variable. And that turns out here, the Fundamental Theorem of Calculus, part 1, doesn't quite apply here yet, because the x here is different from the 4x here. So we're going to have to adapt to this problem. Well, it turns out there's a technique that we used earlier to deal with that situation. Do you remember what was the technique we used earlier when the simple rules didn't work because we had a function of a variable rather than a variable?
Let's see. Sorry, what was the question again?
We've seen that the simple rules for derivatives don't work when you're dealing with a function of variables rather than a single variable. But we learned how to deal with that in our earlier chapters. What was the technique we usually used to simplify functions when the simple rules didn't work at first?
Do we take a limit?
Let's see. Well, we haven't actually had to take a limit to find a derivative for a long time. If any, that would be our last resort because those are pretty time-consuming. Well, for example, there's the power rule apply to this derivative?
It doesn't. We have to use substitution. Chain rule.
The chain rule, yes. So that's the answer to the question that I was asking you a moment ago. What's the technique that we've used in the past when our simple rules don't work? The chain rule. So that's what we're going to use here as well, the chain rule.
Okay.
Let's see. So remember, this is the general way to start with the chain rule.
Mm-hmm.
And the tricky thing here is to figure out who's going to be the outside and who's going to be the inside functions.
Right.
Well, I'll just tell you, it turns out to be convenient here to call the inside function the 4x. So then what would be the outside function?
The inside function is 4x. So the outside function, well, would be, I'm just a little confused. Like 4x is the function we're interested in?
I'm not quite sure what you mean by that. So here's the function that we're trying to take the derivative of. Maybe we should write that like this.
Oh,
Here's the function we're trying to take the derivative of, but this function was too complicated because there was a function of a variable here rather than just a single variable by itself. So we can use the chain rule to simplify things. If we call 4x the inside function, what's left to be the outside function? This was the original function. So 4x is on the inside of that function. What's the outside of that function?
t squared plus cosine of t.
Okay, not quite, because that would leave out this part.
Yeah, I think I'm not quite sure what we're getting at, but
well, what we're trying to do here is apply the chain rule like we have on earlier examples. So in the earlier examples, we saw how we could identify an outside and an inside function, and then we could apply the chain rule to that. So that's what we're doing here. We're trying to figure out what could be an outside or an inside function. Now, what would go in this position then here? Well, this is where the inside function used to be, right? This is the position where the inside function used to be because the inside function is decided as 4x. So what have we done in the past to replace the inside function? If you recall, we've called the inside function u. So this might look different from what we did before, but this is actually pretty much a very similar application of the chain rule to what we've done in the past. We're simplifying this outside function by replacing the 4x just with the u. That's okay as long as we also take the derivative of this inside function. So this is just a pretty normal application of the chain rule. It just looks a little bit different because we never applied it to an integral before.
well, how is 4x the inside function? I'm just trying to make sense.
Well, it's on the inside. It's remember that the technique we did for finding the inside function is to ask how would you do this on your calculator. Well, one way you could calculate this on your calculator is first you could calculate 4x. And then you could plug that into here and figure out the definite integral of this function from 3 to 4x. That was our normal way of determining outside and inside functions before. For example, suppose you were trying to figure out.
Right, like I think I get chain rule. I just don't see how it relates to this problem. I mean, I know it does. I'm just saying that I don't personally see how it relates. I'm just having a disconnect here.
Let's say that you were trying to find the derivative of cosine of 4x. Well, our simple rules don't apply to this. So remember that the trick that we used is to call this the cosine of u times 4x prime. Do you remember how this is how we would use the chain rule to analyze this derivative?
Right.
The advantage of this is now we're not taking the cosine of 4x, now we're just taking the cosine of a single variable. Mm-hmm. Well, if you compare it, that's the exact same trick we're using here. Here we have a function that's too complicated to take the derivative of. So we're going to get rid of the 4x and replace it with just the single variable u. And we call that the outside function. And then the 4x is the inside function. So just like in this case, we had to take the derivative of cosine u times the derivative of 4x. In this case, we're going to take the derivative of this outside function times the derivative of the 4x. The inside and outside just means what do you calculate first and what would you calculate second. If you were going to calculate the cosine of 4x, you could do it in 2 steps. First, you could calculate 4x, and then you could calculate the cosine of that. That's why the 4x is considered the inside function, and the cosine u is considered the outside function. Well, if you were going to figure out this integral, you could do it in 2 steps. First, you could figure out the 4x, and then you could figure out the area of this function between 3 and 4x. So we haven't seen the chain rule used in this particular context before, but it is actually a very similar type of example.
So should t really be u?
Well, the t here, no, the t is not going to change. The t, because the u here stands for the 4x. Remember that we use u to stand for the inside function. In this case, the u, in both of these cases, the u is equal to the 4x. The u is the inside function. So what we're trying to get rid of is this 4x. That's what we're replacing with the u. The t is not going to be altered. The t wasn't the problem with the original problem in any case. The problem was that we had an upper limit of integration that was too complicated. This upper limit of integration was too complicated, so we want to use the chain rule to simplify this part of the function. There's no need to simplify this part of the function because we already have tools for handling that. The part of the function that's too complicated that we need to simplify is this part. So the trick that we use for doing that is we replace the 4x with u, just like we replaced this 4x with a u. But when you do that, you still have to take the derivative of the 4x, just like here we had to take the derivative of the 4x as well. Okay, well I can see how it might be difficult for someone who hadn't seen a problem like this before to come up with this particular way of identifying the outside and the inside functions. But the good news is that all of these problems are going to be very similar to each other. So once we've seen a couple of examples, it won't be too hard to follow the pattern. The pattern is to replace the complicated limit of integration with u, and then treat that as the inside function and also take its derivative. So maybe it's better to keep going forward and show a few examples, and then we'll see how this is used for solving problems. Now, here, what does this prime mean? This means take the derivative. Well, maybe I should have gone back to our earlier example. This symbol means the derivative with respect to x. This symbol means the derivative with respect to x. But what we learned in the past is that this symbol means the derivative with respect to u. When we're using this notation for the chain rule, this is the derivative with respect to u. And we're going to apply that same pattern here. This was the derivative with respect to x. This is a derivative with respect to x, but this is a derivative with respect to u. So let's take those derivatives. Well, maybe we'll start with the easier one first. What's the derivative of this term?
4.
Now, here's the one that's a little trickier. What's the derivative of this term? Well, this might look a little intimidating, but if you remember, this is the exact type of derivative that we learned how to solve using the Fundamental Theorem of Calculus, Part 1. This is the exact type of derivative we learned how to solve using the Fundamental Theorem of Calculus, Part 1. We couldn't apply the fundamental theorem to this derivative because this limit was too complicated. But now with the magic of the chain rule, we've simplified this, so now the fundamental theorem does apply. Of course, now this is a u rather than an x, but what matters is that it's a single variable. So using the approach that we used before, this would now just be the function. Except, since we're taking the derivative with respect to u now, instead of x, we plug in a u instead of an x. just like in this case, this derivative would have been this. If we were taking this derivative, the derivative of cosine u with respect to u would be negative sine u. So similarly over here, the derivative of this integral with respect to u, well, we're just applying the basic fundamental theorem. It's just the function at u. So this is just our general, this is just the fundamental theorem, except we're using u instead of x. Okay?
Yeah, I know we just talked about this, but yeah, so we just rewrote it in terms of u, but on the right, we actually changed, like we really took the derivative. It turned out to be negative sine u.
That's
so
true.
I guess...
Now here we really have taken the derivative too. Why are you saying we haven't really taken the derivative? Maybe because these look so similar. But they're not the same. The way they're different is we got rid of the integration sign. These are not the same as each other. This is the whole point of the fundamental theorem. What's the derivative of the integral of a function? The derivative of the integral of a function is just that function. So we actually have really taken the derivative in both cases. What's the derivative of a cosine? The negative sine. And what's the derivative of the integral of a function? It's just the original function. That was the whole point of the fundamental theorem of calculus. So it might seem at first like we just recopied this, but we didn't recopy it. We made a huge change, which is we took away the integral sign. Okay. Now, it would be a big mistake to stop here, because we need an answer in terms of x, not in terms of our made-up variable u. Well, what are we going to plug in for u here then?
For u, we're going to plug in 4x.
That's what we always do with the chain rule, right? Remember we said that 4x was the inside function. Well, remember at the end, we always plug in the inside function for u. Here again is a case where we need a good use of parentheses. I need to square both the 4 and the x, so I need to put those in a new set of parentheses. And the cosine, I don't need new parentheses. So that's just a very typical example of how we would use the chain rule here. Once we get to this point where we've taken the derivatives, we need to get rid of the u by plugging in the inside function for the u. And I don't think your instructor would require you to simplify this. So we could just stop right here. To carry through the analogy, what you would have done in this case, what would you plug in for u here? You would plug in 4x again. Because I deliberately set up both of these examples to have the same inside function. Okay. So these were kind of similar to each other because they both had the same inside function. The inside function in both cases was 4x. So why did this example seem so much harder and more intimidating? Just because the outside function here was so much more complicated. The outside function here was much more complicated than in this case, but overall the general method here was pretty similar. Okay, so here we ended up with this answer. Okay, well, maybe I'll write down another example.
Yeah, I know this question seemed a bit simple, but I was just trying to get it clear in my head.
Yep, that's definitely important. All right, let's see. This is supposed to be a plus, not a t.
Okay.
And there's not supposed to be any prime there. And it's tricky to write these down without making mistakes. Okay, tell me when you have that written down. Okay, well, I think we'll do one more demonstration project, so I'll do this on my screen here. So here again, we have an area so far function, and we need to take its derivative. So it seems like we could use the fundamental theorem of calculus, part 1. But the fundamental theorem of calculus actually doesn't apply directly to this derivative. Why can't we apply the fundamental theorem directly to this derivative?
Because we have a function of x and not just x.
In the upper limit. Good.
Right.
So I'm going to have to simplify this so that there's only one variable here. Well, the trick we just saw for making that simplification was the chain rule. I'm going to write out each step since we were having some confusion here. It's always good to go in smaller steps. Now, what would be a good thing to use as the inside function here?
6x.
There's many different things you could use as the inside function. Many things you could, but the thing that's useful to use as the inside function is the 6x. Because then that allows us to simplify the outside function. What's the outside function now?
The outside function is 5 plus t cubed plus the natural log of t.
Okay, that turns out actually to be mistaken. There was a huge thing that got left out here, which is the integral sign. Because there's a big difference between the function and its integral. So here's the part that we really want to highlight. The outside function, so the original function involved taking a definite integral. So we haven't done that. We haven't gotten rid of that, so we still need to bring that along. That's the part to especially highlight, because that would definitely mess us up if we left that out. And remember, to have good notation, we always have to put this dt at the end of an integral. We haven't really explained what the dt or dx means here. Well, we kind of have. We said it tells you what variable you're taking the integral with respect to. But it kind of just says, hey, you're at the end of the integral. It's almost like a right parenthesis. The dt is like a right parenthesis that says this is the end of the integral. So we need to include that as well. Now, what am I going to write here?
We're going to write u.
Yeah, perfect. That's the key. Notice if you had left without the integral sign, we don't get to write down that u. The whole point of using the chain rule here was that by treating this as an inside function, we were able to simplify it. Because now we do know how to take the derivative of this. We do know how to take the derivative of this because now the first fundamental theorem of calculus applies, because now this is only a single variable and we're taking the derivative here with respect to u. So what do you think, what would be the derivative of this with respect to u?
Okay, it's 5 plus u cubed plus the natural log of u.
Excellent. Okay, very good. Oh, and then there would be something crucial to remember here. Now, we don't put in the d, because we've now, the point is that taking the derivative gets rid of the integral. Remember that the d is part of the integral. The d is part of the integral. Well, the fundamental theorem says that when you take the derivative, that gets rid of the integral. So what I was saying is what we need to remember is we need some parentheses here, because what goes over here? What's this derivative?
6.
Do you see, if I left out the parentheses, it would seem like I'm only multiplying the natural log times the 6. So I need to continue putting those in. Okay, good. So that gave us this here. Okay, so are we done? Is that the answer?
No, we have to sub 6x in for u, so we can write 5 plus 6x cubed plus the natural log of 6x times 6, all times 6. And now we're good.
Now, I actually made a mistake here. What's the mistake I made in writing this down?
Let's see.
I need some more parentheses.
Oh, okay. Yep. The 6x needs to be in parentheses.
Because otherwise it looks like only the x is being cubed.
Right.
Okay, so oftentimes you're going to have to put in some extra parentheses. And now we can stop. We don't need to simplify this anymore. So this would then be g prime of x. Okay. All right. Now, again, ultimately, these are not supposed to be deep thought questions. And we're not going to worry too much about the meaning of these questions. We're just trying to learn how to get these right mechanically. They don't get any harder than this. This is as hard as they're going to get. So we're basically going to learn a mechanical method for solving these. So what were the things that could give us trouble here? Notice, so what was the outside function here?
The outside function is the definite integral of 5 plus t cubed plus natural log of t with respect to t between -3 and 6x.
Good.
Sorry, between -3 and u.
Yeah, that's right. So what was the mistake that we made before? The mistake was leaving out the integral sign. We can't leave that out. Okay. Now, something else I want to warn you about here that I think would be an easy mistake to make. Notice, we haven't been making this mistake, but maybe I'll just warn you about it anyway. I think it would be very easy here to think that the derivative here is 3t squared. That is, to apply the power rule. But notice it's not. So what's this derivative?
3x squared.
Here's where you apply the power rule. And now this is a very simple example of the Fundamental Theorem of Calculus, Part 1. What's this derivative?
That's derivative is x cubed.
Good. That's good. Excellent. So notice we don't apply the power rule here.
Right.
Because if you kind of think about it, the derivative was already obliterated getting rid of the integral sign. So in a sense, if you see what I'm saying, the derivative never kind of reached the t cubed. The derivative got rid of the integral sign, and the t cubed was just kind of left standing. So we don't want to confuse these two examples. Here we apply the power rule, but the derivative of an integral is just the original function unchanged. Okay? We hadn't been making that mistake, but I could see how that would be easy to have happen. All right? Okay, now it's your turn. Let's try this on your screen.
Okay.
Okay, good. Well, one thing that you did that was very important is that last parenthesis that you stuck in there at the end. We've seen that your graders definitely are picky about those little details. So without that parenthesis, we would definitely lose credit. Because what is the 5 being multiplied times?
The whole it's multiplying the whole thing.
So the point is it's being multiplied times both the 5x to the 4th and the sine of 5x. And without the parenthesis, we can't show that. So that's good that you thought to put that in at the end. That's actually quite important. I guess that's one of these problems are pretty mechanical, actually. So the one thing that takes a little thought is putting in those parentheses. Okay, good. Well, I think that's the right way to attack that. Let's look at that for a moment more, but I think you got that correct. Okay, so like I said, It would be possible to kind of go into the deep meaning of these problems, but that's probably not the best use of our time. We'll just learn how to do them mechanically. I think we've made some progress on that. So let me write down this. Oh, here's a problem. Let's try this on your screen.
Okay, so we can just do. Okay, so since we have the variable as our bottom limit, not a function of x, we can just rewrite this first derivative of g as g, but we replace x for t, and since the x is on the bottom, then we make the whole thing negative. I think that's right.
Okay, very good. Good. So we hadn't talked about that one issue for a second. We hadn't talked for a few minutes about what to do when the variable is on the bottom limit, but you remembered that we have to put the negative sign. And I think it was a good idea to put in that set of parentheses. That set of parentheses helps to show that the negative refers to all the terms, not just to one of the terms. That would be the safest way to answer on the test. Notice this so this is a problem from the website. This is almost like a trap. What's kind of the most common mistake here? I'll bet a lot of people would try to apply the quotient rule here, right? Because they would think they have to take the derivative of that quotient. Well, you can see why it's like a trap, because it's so complicated, you could spend the whole rest of the test, right, taking that quotient rule there. So the point here is you have to know that because the quotient was inside of an integral, we're not actually applying the quotient rule here. We're applying instead the fundamental theorem of calculus, part 1. Okay, perfect. All right, that's exactly right, and you explained what you were doing correctly as well. So I'll go back to my screen. Okay, here's part B of the same problem. Let's try this one.
I'm just doing that for right now. So use triangle. The function is 2x. Outside function is this. I want to use the limit. I take the derivative of this. And 2 minus 3 plus 7 squared is 2. And so solve the inner function back into u. Okay.
Okay. I'm having some trouble seeing your screen, so I'm going to try calling you back.
Okay.
Okay, so let me take a look at what you did. I fell behind there because of the screen difficulties. Let's see. Okay, so one thing that it's good, so let's see. When you plugged in your outside function, at first it looked like you might have been leaving off the prime symbol, but now I can see that you put that prime symbol back in there because the first time you wrote down the outside function, you hadn't taken the derivative yet. It looks like you were careful to use u in the correct places and x in the correct places. Looks like we were careful with the parentheses. Okay, so that all seems like a good approach. Let's see. So point to the 2 minus 2u plus 7u squared term. What was the rule of mathematics that you used to come up with that term?
That's the fundamental theorem of calculus.
That's right, part one
part one
of that theorem. Okay, so that's the theorem that you used at that point in the solution. Okay, all right. Okay, well, I think based on the sample test, you're definitely going to see a couple problems like that on the exam, but I think we understand the basics, so now you can practice that on your own. So I'm sure your instructor assigned you some homework problems for these. So obviously you should do those homework problems, and I've given you the advice in the past, don't just actually do the evens that are assigned, do a bunch of the odds so you can make sure you're getting them right. And then you should be well prepared for that on the exam. Okay, so let's see. Next. So remember that the chain of logic here is kind of a long, subtle chain of logic. We started with a function, f, and then we defined the area so far function, which is basically the definite integral of f. And then when we diagrammed it out, it seemed like f was acting as if it was the derivative of g. And it turns out that Newton and Leibniz proved that that's true. F really is the derivative of g. F really is the derivative of g. Now, remember this problem that we did earlier. So we decided that this was the local max and this was the local min of g. Now, and we decided, more important, this is where g was increasing and decreasing. How did we know g was increasing for this region? So I didn't quite write this the way it is on the sample tests. The way this is written on the sample tests is like this. If you remember this problem that we did at the beginning today. The sample tests ask for a brief explanation of your answer. So you said that g was increasing on this region. Briefly explain, how do you know g is increasing on this region?
It's increasing from, it's increasing a little bit further than that, I think.
Oh, I'm sorry. Yeah, I meant from here to here. Oh, no, you're right. I screwed up. What am I doing? You're right. It's increasing on this region. Thanks. Okay, so how do you know it's increasing on this region?
Because f is positive on that region.
Excellent.
So
I'm sorry, you were saying?
that means g is increasing.
Yeah, we explained why that was. So one way to see why that is remember that g is the area so far. Well, as long as you're adding more positive area, the area so far will keep increasing. That would be good enough for me, but that actually is not exactly what your instructor is going for here. That's not what the instructor wants with this briefly explain. What the instructor wants you to say is this. They want to say, so let's call this, I'll put in some numbers here so I can express this better. I'll call this 4 and 6. So we could say G is increasing on 0 to 4 and 6 to infinity because f is positive on those intervals. That's what you said.
Mm-hmm.
But your instructor wants you to add one more thing. And f is the derivative of g. They want you to add this.
Okay.
Because that's the whole point of these examples, right? The whole point here is to suggest to us the fundamental theorem of calculus, which is that f is the derivative of g.
Mm-hmm.
Remember, that was the whole thing we were getting from this, that f is acting like the derivative. So your instructor wants you to actually say that explicitly for full credit on these types of problems. Okay, so we will learn to satisfy their expectations on that. So here's what they're going for. They want you to say g is increasing because f is positive, just like you said before, but then you have to add one more thing. What does it matter why f is positive? Well, it's because f is the derivative of g. So notice then the whole point here is, obviously, so this basically means where f is positive, that really means g prime is positive, right? Mm-hmm. And we know from earlier that when g prime is positive, g is increasing. F is positive here, that really means g prime is positive, and where g prime is positive, g is increasing. All you have to do is just add this one little phrase here, though. Just point out that the reason why it matters is because f equals g prime. Okay, so for example, suppose they had asked you, where is g decreasing? Where is g decreasing? Briefly explain. What would your answer be?
Okay, so g is decreasing from 4 to 6, and it's decreasing because f equals g prime.
Okay, now that's only half of it. Why does that mean g is decreasing and not increasing?
Because g prime is negative.
Yeah. And f is negative on 4, 6. So you have to include both of those parts. You have to say, okay, after all, how did you know originally that g was decreasing here? You knew originally that g was decreasing because f was negative. But why does it matter that f is negative? Because f is the derivative of g. So we need to include both of these in the answer. All right, so where is g increasing? Where is g increasing here?
G is increasing from...
And briefly explain.
Let's see. A to 4.
Yeah. I should have said, let's call that 2.
Okay, from 2 to 4. And 6 to infinity. And it's increasing on those intervals because f equals g prime and f is greater than 0 on those intervals.
Good. You don't need to say this, but that means that g prime is positive, and when g prime is positive, g must be increasing. But this is all you need to say. Okay, good. So, so that's just a little extra detail that we'll need for full credit on those types of problems that we were working on before. Based on the sample test, you're pretty sure to see something like this on the test. Mm-hmm. Okay, very good.